afternoon. Okay, any questions on the first part of Chapter 4 that we covered on Friday? Before we move on.
I don't think so.
Not for you, okay. Anyone else?
No, I think we're good.
Okay. All right. Now, I spoke to Distance Ed this morning. They gave me a different way of connecting to the PowerPoint. So, this might go squiffy to begin with. Why is that not working? The entire screen. See, that's the problem. It doesn't work the same way here as it does on the laptop. It said share entire screen. That entire screen is the last option on the drop-down for the application when you do it on the laptop.
Did you get to click on that screen itself? Yeah. And share audio if you want to.
Okay. So he said if we do it this way, then when I go here, yes. Okay. Finally. All right, so we're just going to finish a little bit of information on the organization. Oops. Remember that we have the peripheral nervous system is divided into the autonomic and the sensory. The autonomic is divided into the sympathetic and the parasympathetic nervous systems. And it's responsible for all those kind of unconscious type controls, heart rate, breathing, digestion, etc. The sensory nervous system is responsible for kind of tying together the information from the external, from the environment, and then the response to that information. So we've got a sensory division, so the nerves that leave any sensory receptors that we have and go to the central nervous system. And then the motor division is bringing the signal from the central nervous system to the muscle in response to the sensory information. So within the nervous system, there are a couple of opportunities for fatigue to occur. Okay, one that they assume is going to play a role is the person's determination to get the movement done, right? So that will drive the strength of the signal being sent, in a way, right? And then we have the motor output, so the signal down the motor neuron, and as you'll see before we finish today, there's quite a lot of chemistry involved in that, and so it only takes for there to be a little bit of imbalance in the chemistry, or for one thing to be a bit low in availability, for that signal to get slowed down, and then that would slow down the signal to the muscle. All right, when we look at this diagram here, the peripheral fatigue is, I think, probably a little more understandable, and it relates to the next chapter when we're looking at how does the muscle contract, how does the signal stimulate contraction in the muscle. So this bottom half of this diagram will make more sense when we do chapter 5, and we'll come back and have a look at that. All right, the central fatigue is very hard to test for. So a lot of it is hypothetical at the moment, but with more and more sophisticated equipment, I think we'll learn a lot more about what could be causing fatigue within the nervous system, right? From the point at which the brain decides it's going to do the skill to the signal reaching the muscle. What's going on there that could be a site for fatigue? Okay. So we've got to talk about our motor nerves and the way that they stimulate muscle fibers. All right, so the muscle cell is a functional component, right? And it responds to an electrical signal that's under direct neural control, okay? So it's gonna contract when it's given a signal to contract, okay? So when we look at a motor neuron talking to muscle fibers, all right, then what we see is that one type of motor neuron connects to a number of motor fibers. That's called a motor unit. So a motor unit is an alpha motor nerve, and all the muscle fibers that it connects to, that it stimulates. Right? So one of the weird things about them flipping these chapters around, whilst I think it seems like the right idea to me that we say how the signal gets to the muscle before we talk about the muscle, but when we do it this way around, we don't have this understanding of the muscle cells. Right? So the muscle cell is a muscle fiber, and one muscle is made up of many, many, many fibers. Okay? So the unit on the left is stimulating fiber 2, 3, 5, and 6. And the motor neuron on the right is stimulating fibers 1, 4, and 7. Okay? So these motor units have classifications based upon the how easily they fatigue, and it also relates to which energy system they're good at using. Right? So an S motor unit, S is for slow, right, is going to stimulate muscle fibers that are type 1. Okay? They're very, very good at using Krebs cycle and the electron transport chain. They're very good at using oxygen to make ATP. All right? They're the smaller kind of motor nerves. Okay? They have a slightly smaller cell body, which means they're a little bit easier to stimulate to reach threshold at the axon hillock. The next category of motor units is called an FFR, F for Freddy, FFR. That stands for fast, fatigue, resistant. Right? So they stimulate one of the type 2 muscle fibers, and they stimulate the ones that are type 2A. Type 2A fibers can use oxygen, although they're not as good at it as type 1s. And they're also quite good at creating ATP without oxygen. Okay? So they're good at glycolysis, right? Our third category of motor unit is an FF, and that stands for fast fatigable, right? So that type of motor unit is going to contain type 2X muscle fibers, all right? The ones that really can't use oxygen well at all, and they rely on glycolysis and predominantly ATP-PC because they can contract very rapidly, right? So they need to be able to contract without oxygen and as quickly as they can. Does that make sense? So when you look at this diagram, one of the things you have to really get your head around here is it isn't the muscle that is a type 1 or a type 2, right? It's the muscle fibers related to a particular motor unit that are a type 1 or a type 2, right? So when we look at this diagram, the motor neuron number 1 on the left could be an FFR, and the motor unit on the right could be an S within the same muscle. But the fibers that that motor neuron stimulates can only be type 1s if they're in an S unit, right? And these muscle fibers that are stimulated by motor neuron number 1 can only be type 2s if they're being stimulated by an FFR. Questions? No? All right, so this is just a diagram to make it easy to understand. The number of muscle fibers that a particular motor neuron can stimulate is dependent on how much control that muscle fiber needs. Okay? So if it's stimulating the muscles that move the retina or stretch your retina, move your eyes around, right? Very fine motor control. We see the motor unit connect to less muscle fibers. So in the eye, the motor unit may only contain 5 to 10 muscle fibers in it, right? But a motor unit down in our calf muscle, where that contraction doesn't have to be very precise, right? We just want a lot of oomph in it. Then the motor unit might contain up to 1,000 muscle fibers in one motor unit, right? Our textbook tells us that on average, when we look at all the motor neurons throughout our whole body, on average, the unit contains about 100 muscle fibers. Although I have to say that number, personally, that doesn't really mean very much to me, because if we can go all the way from 5 to 1,000, then I'm not sure what good it does me knowing that average is 100. Do you get what I mean? So I personally don't find that number particularly useful in this situation, because I think I want to know that the motor units in my eye have a really small number of muscle fibers. whereas the ones in a larger muscle can have a very huge number of muscle fibers, right? That seems to me to make more sense. But as you go through the chapter, you take the information the way that it makes the most sense to you, okay? All right, so a motor unit then, to review. Motor unit is a motor neuron and all the muscle fibers that that neuron synapses with and stimulates, okay? Now, when we look at the muscle as a whole, right, the muscle as a whole has lots of these motor neurons coming in and stimulating muscle fibers, right? That's how the brain controls force production within a muscle, right? How many motor units do I turn on? How many muscle fibers do I contract? Right? So when we look at the muscle as a whole, we have what they call a motor neuron pool for that muscle. And a motor neuron pool can combine S, FFRs, and FF motor units. All right? Because a muscle isn't slow or fast. The muscle fiber is slow or fast. The muscle itself has both types of fibers in it, right? And then it depends on how much, what's the ratio of one type to the other type as to what that muscle is capable of, right? So a motor neuron pool can contain all three types of motor units. But a motor unit can only contain one type of muscle fiber. Questions?
No.
No? Okay. All right. Now we have to do a little bit of the chemistry stuff. I keep it as basic as I can. All right. So technically it's a lot more complicated than the information we're going to do, but I think the level that we do it at is really, it's just enough for you to be able to understand what's happening without having to get too deep into all the chemistry and things that we don't need, okay? So, some terminology to begin with. We've already looked at the term action potential and impulse. That's the electrical stimulus that's coming down from the central nervous system to the motor neuron and then out to the muscle, all right? That action potential. And remember that we talked about the fact that the dendrites of the motor neuron all receive action potentials, and then at the hillock, those potentials are all summated, and if they're big enough, then it sends the signal on down the axon. Okay? Resting membrane potential, when you look at an electrically excitable cell, so the heart muscle, the nervous tissue, skeletal muscle, they're all electrically excitable. It's literally like taking a voltmeter and sticking it into a plug hole kind of thing, right? There's real electricity there that you can measure with the right equipment, all right? So when the nerve or the muscle is at rest, right, then there's no impulse being conducted at that point. And the measurement, the voltage, is about minus 70 millivolts for a motor neuron. Okay? And we have minus 70 because the balance of charged ions on the inside and the outside of the cell aren't balanced, aren't level, right? So inside the cell is a negative charge compared to the outside of the cell that's a positive charge. Okay. And so in order to initiate the action potential, we have to upset the resting membrane potential, the RMP. Okay? And the way that is done is by depolarizing the membrane. Right? So when we depolarize the membrane, we open channels in the membrane like little gates. Right? It's like just like a gate, a sodium gate. And sodium can flood into the cell from outside the cell. And so sodium is a positive charge, and so as it floods into this more negative environment, it upsets the balance across the membrane, right? Changes the balance. And once we've done that, then we have to get the membrane back to resting membrane potential for the next signal to come down the motor nerve. Because one signal, right, it doesn't do me any good if I'm in Walmart and I take one step and I stop. Right? There has to be continual signals from the central nervous system for me to walk around. Okay? So we have to, once the membrane has depolarized, it can't accept another signal without going back to rest first. Okay? So from depolarizing, we then have to repolarize to get it back to rest. And when we repolarize, we close the sodium gate and we open a potassium gate, and potassium can leave and go outside the cell. Potassium's positive. It changes the balance of the charge across the membrane again. Okay. So when we look at, okay, so here's, on the left is a picture of the gates, the channels, right? So when we depolarize, we open the sodium channel and sodium ions flood through, they're positive, they change the charge across the membrane. When we repolarize, we open potassium channels and potassium floods out and again changes the voltage across the membrane. Right? I think this graph is really useful personally, okay? So let me talk you through here because it gives you an indication of just how small, how short this depolarization, repolarization period is, all right? So here's repolarizing, right? Here's threshold. So once we hit threshold, that action potential is going. Okay? So you can see it goes from around, on here they have minus 65, so here's minus 70, right? So we said about minus 70 millivolts at rest. It shoots up to 30 millivolts, and then we have to repolarize it so the next signal can be accepted. So we repolarize, and what happens when we repolarize is we overdo it here, and so then we have to move some sodiums out and some potassiums in to get us back to resting membrane potential. For those of you that are interested in the detail, it's 3 sodium out and 2 potassiums in. But I wouldn't worry too much about that unless the detail helps you. Okay? And then we're back at rest, and we can accept the next action potential for the next muscle contraction. if you look along the time here, right, it's just a few milliseconds, just a couple of milliseconds for that whole thing to happen, right? Not even 3, because by the time we get to 3 milliseconds, we're basically back at rest. Okay? So one of the things that it's important to understand here is that opening and closing these channels, these ion channels, takes a lot of energy. So when we are making ATP, nearly 50% of that ATP is being used to open and close these ion channels to get the signal to the muscle to contract. Okay? So if you think back to the epoch graph, right? And we were looking at what's going on in epoch, that means we have to keep breathing so deeply for so long after we finish the exercise. One of the things we have to do is to use ATP to put all the muscle tissues back to resting membrane potential. Right? Okay, so remember we've got an action potential is electrical. It's going to come down the axon of the motor nerve. When it reaches the neuromuscular junction, we can't transmit electricity across a gap. So it stimulates the vesicles to release ACH. ACH floods across the gap, attaches to receptors on the muscle surface, and if there's enough ACH, then it initiates another electrical action potential across the surface of the muscle. Electrical, chemical, electrical. Right? So ACH happens to be a neurotransmitter that is of the type that we call excitatory. All right? It's responsible for turning that muscle on. Right? It's part of turning the muscle on. There are other types of neurotransmitters that are inhibitory. So when we looked at that reflex loop and we said that there was an inhibitory motor neuron to the hamstring, then it releases, well, it's slightly different with the hamstring. It doesn't release ACH. But in certain circumstances, there's going to be an inhibitory neurotransmitter. Questions? That's as much chemistry as my brain can manage. So I'm not going to do any more chemistry per se. All right. So way back at the beginning, we said that one of the types of cells within the nervous system were neuroglia, right? And the myelin sheath that plays an important role in the motor system is part of the neuroglia, right? It's a fatty substance, and it's wrapped around the axon of the motor nerve like a blanket, right? But instead of being one blanket all the way down the axon, it's lots of little blankets wrapped around. So there's a gap in between each myelin sheath. Okay. The gap is called the node of Ranvier. And what that allows for is much, much faster conduction of a motor signal down that axon. Because where the myelin is wrapped around, the electricity can't get to the membrane of the nerve, so it has to jump over the myelin to the next gap in the myelin, to the next node of Ranvier. And this is called saltatory conduction. Let's see if I can do a not very artistic interpretation for you. Oh gosh. Okay. So here's my motor neuron. Right? And wrapped around the motor neuron is this fatty substance. And so what that means is that my action potential travels along this part of the nerve, and then it has to jump to here. Travels along, jumps, travels along, jumps, travels along, jumps. And that speeds up this transmission because it doesn't have to use all this energy opening and closing sodium and potassium channels, right? It just jumps over to the next bit. So that can speed up conduction of a motor signal up to 150 times faster than a nerve that does not have myelin wrapped around it. So it seriously speeds up that signal, right? So that's a major advantage of saltatory conduction, right? Because if it took forever for that signal to get from the spinal cord out to the neuromuscular junction, we'd be walking around like robots, right? We wouldn't be able to have the very fluid, very subtle movement patterns that we have. Okay? So it conserves energy because I'm not having to use this ATP to open and close sodium and potassium channels, and it increases the speed at which the signal can get from the cell body in the spinal column out to the neuromuscular junction. So we've got the signal, right? And we've got some idea that the central nervous system can turn on certain motor units and not other units, depending on what the job the muscle is being asked to do, right? How does that happen? Okay. So we want to be able to regulate the number of motor units that is turned on and the size of the motor units that are turned on if we want to control force. Right? There wouldn't be any point in me turning on 100% force to pick a pencil up off the table. Right? I don't need that much force to do that. So how does the central nervous system control these motor units? Right? So the primary way it does it is by the size principle. Okay? So by the size of the actual neuron, right? Motor units are typically recruited from the smallest neuron to the largest neuron. Remember we said that the S motor unit has the smallest cell body. So we go from S to FFR to FF. Right? So that means that we go so much easier when you guys are in the classroom and I can just scribble on the whiteboard. So we go from slow to fatigue resistant to fast fatigable. Smallest to largest. Right? And that is going to relate when we get to chapter 5 to type 1 muscle fibers, to type 2A muscle fibers, to type 2X muscle fibers. Alright? So a good example here from a movement perspective is if you're training a female and she says, well, I don't want to get big muscles, right? And you can go through the whole explanation of you won't get big muscles because you're a female and you don't have enough testosterone, and etc., etc. But another way of explaining it is that if you think about runners, right? Think about the size of the muscles on a long distance runner compared to the size of the muscles on a 100-meter sprinter, right? So that's because one of the reasons is because the long distance runner turns on lots of S motor units to achieve their job, right? And type 1 muscle fibers do not grow in size as well as type 2 muscle fibers. A 100-meter sprinter has to turn on lots of FF motor units, lots of type 2X, and so they get lots of growth in size of their muscle fibers, right? So if I give a female a training program with relatively lightweight and more repetition, she's not going to turn on the kinds of muscle fibers that are going to grow and give her big muscles, assuming that she was cheating and taking steroids or growth hormone or something, right? Okay? So jogging doesn't create big muscles. Resistance work with your body weight or with resistance bands or light weights does not develop big muscles because they're not turning on those kinds of motor units. Okay. Now, that's the principle. And as with most principles and rules and laws, there's an exception, right? There's always an exception. And so here, the exception is to do with the goal of the movement pattern, right? So if I'm a sprinter, whether I'm a swimmer or a runner, right, and the gun goes off to start the race, and I have to turn on my slow motor units, then my fast fatigue resistance, and then I get to my power, it would take 25 seconds to run 100 meters, right? So there are situations where either we train to jump the size principle, right? Because it's detrimental to the performance. I need to be able to be on my blocks, gun go off, power out as fast as I can. Right? if I've got that kind of power. Okay? So that's why sprinters take a long time to practice starts, right? And it's why there's some strategy, particularly in a race that's longer than 100 meters. But even sometimes in 100-meter races, you can see, you know, this person knows they're going to be a little bit slow out of the blocks, but they also know that they can power through at the end of the race. Or you've got a runner who's very, very quick out of the blocks, but then you've got to train them to hang on long enough to get to the end of the 100 meters. Right? Depends what their body type is. Okay? So we can override the size principle with training, or the other situation where we can override the size principle is in situations of danger, right? And sometimes we read those odd stories where the mum realizes that the car is rolling back and it's going to run over the baby, and she can stop the car or pick the car up so the kid can get, right? How does this little tiny woman pick up a car? Right? Because in that situation, adrenaline and everything else kicks in and bypasses the size principle. Okay? So the size principle is important. The other law that's important is all or none. And what that means is, if we go back to our, if we go back here, that means that if that axon hillock stimulates an action potential, every fiber in that motor unit will contract. It's all or none. If there's an action potential that reaches threshold, they all will contract. If the action potential does not reach threshold, none of them will contract, right? You can't contract just one muscle fiber in a motor unit. Either the whole unit contracts or the whole unit doesn't contract. So there's lots of benefits to this idea, right? It means that my most easily recruited motor units, right, my S, are predominantly the first ones to turn on, right? So for endurance activities, for everyday living type activities, we don't have to use all this energy to turn on the larger motor units. I can get most things done turning on my smaller motor units. And that delays fatigue, because it means I've got more energy left over and I can keep going for longer. So here's the same idea in picture form, if you're better off in picture form, right? So I have a job to do, and so following the size principle, we turn on our slow motor units. But the job really isn't finished, it's not getting done. So we have to resort to turning on the next level of motor units. And then if we really have to, we'll turn on the third level of motor unit if we need that much oomph to get the job done. Okay, so what adaptations do we see in the neural system then? right? Because we said that, if we're training and we're seeing improvement in performance, then there's adaptations that are occurring in response to the stress of the training that benefit my performance at that particular task. Right? Typically, adaptation is positive. Okay? So what we see in the neural system, we may see some remodeling of the neuromuscular junction. So the size of the vesicle and the size and number of the postsynaptic receptors for the neurotransmitter can increase anywhere up to about 15%, right? So if I've got bigger vesicles, then they're going to store more ACH, which means I'm going to reach threshold faster as the ACH floods across the gap. Okay? We can see increased contraction to any submax level of neural drive. So neural drive is initiated in the central nervous system, and it's a measure of motor unit recruitment and the rate of turning them on, right? So how many and how fast do I turn on the motor units, all right? So I can alter, that means that I'm able to alter the rate of action potential generation, right? I'm able to speed that up. So that increased response to neural drive could be due to improved activation at the muscle, but more likely it's a more efficient recruitment pattern. So if I'm doing strength and power work, right, if you think about it, if I'm doing strength and power work, then I want to be able to turn on as many motor units as possible at one time, right? I want the most amount of force production at one go, right? So if we do strength and power training, then it seems most likely that what we get are more efficient recruitment patterns, right? We turn them on, we see more synchronicity. Then when we look at maximal neuronal drive, so if we look at a 1RM test, okay? So this is really interesting. Okay, if you look at this graph, the blue line, this blue line, indicates improvement in strength, which we would measure using a 1RM. So here's right at the beginning of the training program, and this is looking at the studies that are in the literature. Most of the studies are around 8 to 12 weeks, usually around 8. It's difficult to collect data for 3 to 4 months because so many people drop out, right? So in 8 weeks, we see this very steep increase in strength. But the green line represents muscle hypertrophy. And in 8 weeks, we see not very much increase in muscle size. So where did all this increase in strength come from? Right? And what's really interesting is that initially, the changes in strength are due to adaptation in the neural system without adaptation in the muscle fiber. Right? Which is pretty cool. Okay? And then when we look at declines in strength due to taking time off from training or due to getting older, then the decline is also more due to a decrease in neural drive than it is to a decrease in size. Right? So, you know, it's kind of abstract. We can't see nerves the way we can see muscles, but they play such a huge role when we're looking at strength and power training. Okay, so I have a little bit more on adaptations to strength and power training and a little bit on adaptations to endurance training. So we'll do that on Wednesday before we start chapter 5. Okay? Any questions on that info from today? It's very cool. The neural adaptation information is just mind-bogglingly fun, I think. But then I am a bit of a geek. But yeah. Questions, comments? No? Okay, make sure to review a little bit before Wednesday. Then we'll finish off the last couple of slides on chapter 4 and we will start chapter 5. Okay? I have office hours this afternoon. If you've got other questions, you can jump in and see me in office hours. Otherwise, I will see you Wednesday.